Precision recall curves are a very widely used evaluation method for machine learning. As we just saw in the example, the x-axis shows precision and the y-axis shows recall. Now, an ideal classifier would be able to achieve perfect precision of 1.0 and perfect recall of 1.0. So the optimal point would be up here in the top right. And in general, with precision recall curves, the closer, in some sense, the curve is to the top right corner, the more preferable it is, the more beneficial the trade-off it gives between precision and recall. And we saw some examples already of how there is a trade-off between those two quantities, between precision and recall, with many classifiers. This example here is an actual precision recall curve that we generated using the following notebook code. The red circle indicates the precision and recall that's achieved when the decision threshold is 0. So I created this curve using exactly the same method as we saw in the previous example by looking at the decision function output from a support vector classifier, applying varying decision boundary, and looking at how the precision and recall changed as the decision boundary changed. Now, fortunately, scikit-learn has a function that's built in that does all of that, that can compute a precision and recall curve. And that's what we've been using in the notebook here. So you can see that in this particular application, there is a general downward trend. So as the precision of the classifier goes up, the recall tends to go down. In this particular case, you'll see also that it's not exactly a smooth curve. There are these sort of jaggy areas here, and in fact, it gets sort of the jumps tend to get a little bigger as we approach maximum precision. And this is a consequence of how the formulas for precision and recall are computed. They use discrete counts that include the number of true positives, and so as the decision threshold increases, there are fewer and fewer points that remain as positive predictions. So the fractions that are computed for these smaller numbers can change pretty dramatically with small changes in the decision threshold. And that's why these sort of trailing edges of the precision recall curve can appear a bit jagged when you plot them. ROC curves, or receiver operating characteristic curves, are a very widely used visualization method that illustrate the performance of a binary classifier. ROC curves on the x-axis show a classifier's false positive rate, so that would go from 0 to 1.0. And on the y-axis, they show a classifier's true positive rate, so that would also go from 0 to 1.0. The ideal point in ROC space is one where the classifier achieves 0, a false positive rate of 0, and a true positive rate of 1. So that would be the upper left corner. So curves in ROC space represent different trade-offs as the decision boundary, decision threshold is varied for the classifier. So just as in the precision recall case, as we vary decision threshold, we'll get different numbers of false positives and true positives that we can plot on a chart. So the dotted line here that I'm showing is the classifier curve that results, the ROC curve that results from a classifier that simply randomly guesses the label for a binary class. So it's basically like flipping a coin. So if you have two classes with equal numbers of positive and negative instances, then flipping a coin will get you randomly equal numbers of false positives and true positives for large data sets. So the dotted line here is used as a baseline. So a bad classifier will have performance that is random or maybe even worse than random, or maybe slightly better than random. A reasonably good classifier will give an ROC curve that is consistently better than random across all decision threshold choices. And then an excellent classifier would be one like I've shown here, which is way up and to the left. This particular example is an example of a logistic regression classifier using the notebook example that you've seen. So the shape of the curve can be important as well. The steepness of the curve. We want classifiers that maximize the true positive rate while minimizing the false positive rate. Now, as we'll see next, we can quantify the goodness of a classifier in some sense by looking at how much area there is underneath the curve. So the area underneath the random classifier is going to be 0.5. But then the area, as you can see, the size, the bumpiness of the classifier as it approaches the top left corner, the area underneath the curve will get larger and larger, and it'll approach 1. And so, as we'll see in the next slide, we use something called area under the curve, AUC. That's a single number that measures this total area underneath the ROC curve as a way to summarize a classifier's performance. So an AUC of 0 represents a very bad classifier, and an AUC of 1 will represent an optimal classifier.